Greetings everyone, this is the IBBT plan presentation for the Drone Food Delivery System project. The team members for this project are Hernan Valenzuela, myself, Edward Gonzalez, Mariana Hermosillo Hidalgo, and MD Abubakar Siddiq. The agenda for this presentation includes introduction to the project, reference documentation used in the project, some key terms, acronyms, and definitions, project teams organization and management, a review of the PBT evaluation tools used, project PBT activities throughout the different phases, definition, design, implementation, integration, qualification, and post-development, and finally, conclusions, discussions, and reference used. The integration, verification, validation, and testing plan serves to evaluate and validate the system across its development stages. It outlines the various forms and methodologies employed for this purpose, as the name suggests, by verifying, validating, and testing the drone food delivery system. It specifies the activities to be carried out and the techniques utilized to prioritize these activities. The verification process activities will determine if the system was implemented correctly, while the validation process activities will determine if the system delivered meets the customer's requirements. The BBT team will review these documents to ensure total accuracy and fulfillment of the requirements. The drone food delivery system, as the name suggests, is a food delivery system performed by drones. It integrates drones equipped with sensors and GPS for near real-time tracking. These drones will receive coordinates and food pickup details from restaurants through a dedicated mobile application, which will have algorithms to optimize the drone paths. So, the drone food delivery system will reduce operational costs by minimizing workforce, eliminating vehicle fuel expenses and vehicle maintenance, and also it will reduce road traffic. These tables show the key personnel, project role, contact, and project scheduling. We chose Wednesdays after 8:50 p.m. after class as our main meeting time and Saturdays at noon as our backup meeting time. Listed here are the reference documents throughout the project, the documents created during the project, and the reference used for the creation of these documents and the BBT activities. The most relevant key terms and acronyms used in this project and their definitions are listed in the following table. The following scheme shows a representation of the team's organization. Each team member is responsible for executing the assignated task associated with the respective role. Additionally, as a team, we consider not only the direct members introduced previously, but also our faculty supervisor and other group team members for the active feedback on our project. Here, it is detailed the responsibilities of each team member by the given role. The following shot shows the drone food delivery system project master schedule. The purpose of risk management process is to identify, assess, prioritize, and mitigate risks that could potentially impact an organization's objective. By effectively managing risks, organizations can minimize potential negative impacts, seize opportunities, and also achieve their goals more successfully. It is an ongoing endeavor that systematically addresses risk across the life cycle of a system, product, or service. This process is applicable to risks associated with the acquisition, development, maintenance, or even the operations of a system. First, this risk matrix, developed in our cost-benefit analysis, summarizes the highest priority risk within each category and ranks them accordingly. It includes the probability of failure and severity level for a total indicator. Additionally, it outlines the potential impact on the system in case of harm. A color-coded system, red for high risk, yellow for moderate risk, and green for low risk, is used to indicate the overall risk, which guides the planning of preventing actions, like including additional testing, redesigning, or improving the process itself to mitigate or eliminate a risk. This section outlines the criteria for logging defects discovered during requirement development. It covers grammar to ensure correct spelling, consistency to maintain project integrity, ambiguity to ensure clarity, completeness to capture the entire point, and organization to maintain logical formatting. So the defect log itself serves to catalog all defects encountered during the project development phase. It's crucial to document the time invested in rectifying these defects to ascertain the engineering cost associated with their solution. It's important to note that both these checklists and defect logs are also part of peer review activities. For the requirement verification matrix RVM, it typically includes a unique requirement identification code on the RVM, a code for traceability on requirements for higher level documents, a description of the requirement, the stage at which verification occurs, level at which the test is going to be performed, being component, subsystem, and or system, and finally methods for verification and identification code for these methods, being the most common but not limited to analysis, inspection, demonstration, testing, and certification. The requirement bidirectional traceability matrix ensures that all products requirements have been fully addressed and can be traced back to its valid source. Traceability is essential for establishing the connection between each individual product level requirement and its origin. For this, the RBTM offers two key functions. It provides a means to trace from a requirement to its implementation, and it facilitates tracing back from an element in the implementation to its original requirement. In this sense, the RBTM plays a vital role in the BBT processes by ensuring that all requirements are allocated during production and that each component, subsystem, and element of the product is indeed necessary. Failure mode effect analysis is a systematic approach used to identify potential failure modes within a system or process and develop strategies to mitigate them. The process involves identifying possible problems, their causes, and their potential impact on the system or process. These potential failures are then prioritized based on their probability, frequency, and severity. And it finally aims to take proactive measures to eliminate or reduce the occurrence of future failures.
In the project's definition phase, the initial step is to establish the overall BBT management plan. This plan serves as a comprehensive framework delineating critical activities across different project stages. Here you can find a range of activities including system ConOps, system requirements, defect log, RVM, cost benefit analysis, component test document, integration test description, IPP plan, and others, along with the respective start and deadline dates. By delineating these key elements, the BBT management plan ensures clarity and structure in the project execution, facilitating efficient progress tracking and timely completion of the milestones. The operational concept for our drone food delivery project entails a streamlined process beginning with customers placing orders through designated restaurants via an online platform or app. Once an order is placed, the drone promptly receives a notification detailing the specifics of the request. Subsequently, the restaurant prepares the orders swiftly, triggering the drone's movement towards the restaurant or a predetermined pickup location. Upon arrival, the drone collects the order and embarks on its delivery route, navigating to either the specified customer location or a predefined hub for the order collection. Upon reaching the destination, the drone executes a safe and efficient delivery either directly to the customer or to the designated pickup hub. This structured approach ensures the seamless and timely delivery of food orders, leveraging drone technology to enhance overall customer satisfaction and convenience. Within our drone food delivery project, we have outlined a total of 23 requirements, initially suffering from a lack of clarity. However, through meticulous feedback from instructor and peers, we have successfully standardize them. Each requirement is now well defined and categorized into functional, communication, or performance level. For instance, requirements number 3, falling under the functional category, explicitly states that the system hardware should not experience more than one mechanical failure per 100 hours of operations, providing a clear target. Furthermore, we have considered regulations governing drone systems in selecting communication category requirements. Additionally, within this category, we have addressed how the drone interacts with the customers under various conditions and its communication protocols with the business and customers. Critical performance level requirements cover drone weight capacity, battery performance, path optimization, and its ability to operate in adverse weather conditions, ensuring a comprehensive approach to project fulfillment. Following the acquisition of system requirements, the focus shifts to developing the requirements verification matrix for the drone food delivery system. Within this matrix, each requirements is assigned a unique traceability ID along with a predetermined verification stage. For instance, requirement 7 involving the real-time communication of battery charge percentage to the business via the app every 10 seconds is designated for implementation phase of the verification stage. Notably, this requirement operates at the subsystem level, necessitating interface testing for verification as indicated by the symbols representing various testing methods located in the top left corner of the slide. During the design phase, the initial step involved conducting a comprehensive analysis encompassing cost, benefit, and risk assessment. Numerous risks are crucial for meeting customer needs in the drone food delivery project or identified. This critical risk pertain to the availability of drones, external factors such as weather condition, issues related to low battery performance, potential malfunctions in sensors, essential to this process was estimation of costs associated with BBT as well as appraisal and impact cost, which played a pivotal role in determining the risk values attributed to the various challenges inherent in drone food delivery. Here you can see a portion of cost benefit analysis for our project. Its risk is meticulously evaluated based on its probability and severity rated on a scale of 10. The risk value is derived by multiplying these two factors, effectively prioritizing risk according to their potential impact. Notably, risk 2 concerning drone being affected by external factors emerges as the most critical, with a risk value of 63, necessitating immediate action during VBT phase to mitigate potential consequences, as allowing it to persist into the final product would result in the significant impact cost. Conversely, risk 12 involving damage or loss of delivery packages carries a lower risk value of 7, indicating a lower likelihood and impact, thus allowing it to be deemed acceptable without intensive focus during the VBT stages. Validating system design tools involves confirming their suitability and functionality for intended use, ensuring personnel are promptly apparent. We maintained a defect log for drone food delivery, noting issues from checklist assessments and instructor and peer reviews to enhance the reliability and project success. During the design stage, a critical task involved developing a requirements bidirectional traceability matrix for the drone food delivery project. This matrix vertically listed project requirements and horizontally listed necessary elements for each requirement, facilitating interpretation in terms of both forward and backward traceability. For example, requirement 3 specifies that the system hardware should not encounter more than one mechanical failure per 100 hours of operations. Elements essential for fulfilling this requirement, such as cameras, mechanical flying system, motors, sensors, and power monitoring software, are outlined within the metrics, establishing their relationship to forward and backward traceability as demonstrated in the slide.
My name is Edward Gonzalez, and I will be discussing the implementation and integration sections of this presentation. This slide lists out the component test plan, high-level goals such as the approach, the specifications of requirements, and the testing strategies. These will be detailed out later throughout the presentation. This document serves as a guideline for various stakeholders to ensure that tests are being evaluated correctly as intended. The main objective is to ensure that the battery is operating as required so that the drone delivery system can be successful in all aspects. It is vital the battery goes through robust and thorough testing, as it is the single most important component of this system. Before the testing begins, there needs to be strict preparation for the test to ensure that all the data is collected the same and is standardized in the output. It is vital to ensure that the lithium polymer battery has passed quality test and is not defective. This is so the team gets an accurate output after the tests are being conducted. The battery will be charged to its full recommended capacity before every test by using a compatible charger to ensure the battery does not degrade more than it should. The simulation environment will be set up to mimic whatever test is being executed. For example, if the drone will be carrying a 15-pound of food and needs to deliver a package in less than 15 minutes, the drone may need to move at an average speed of 30 miles per hour. The weather will then be accounted for and then tested. Temperature sensors will also need to be calibrated as well. This is to ensure that the test is being followed as planned. The primary test that the team is to focus on is the endurance of the lithium polymer battery. The tests are measuring consumption for different scenarios the drone may experience in a real-world scenario. These measurements are to be documented and saved for further analysis. The criteria for this test has various variables that need to be accounted for to make sure that the drone doesn't fail in the real-world scenario. Assumptions. While conducting the simulation and the test, there is an assumption that the software accurately represents real-world conditions. There will be a high confidence in the data output when doing further analysis when determining how much energy is required. Constraints. Safety is a top priority when conducting these tests and also when the drone is operating in the real world. The test will adhere to all safety protocols and regulations. The chart on the right illustrates how the information will be documented and saved. This slide details out the component test inputs. The load weights being tested are listed as 5, 10, and 15 pounds. The speed at which the drone will be flying is 15, 30, and 45 miles per hour. The test will be using this speed as an average throughout the entire simulation of the test. The three weather conditions being focused during these tests shall be 1. Clear, 2. Rainy, and 3. Windy. These weather conditions will also have mixed simulations, such as rainy, rainy and windy, clear, clear and windy, etc. The temperatures that will be simulated at 20, 60, and 85 degrees Fahrenheit. This is important to understand since the colder weather will most likely require more energy for the drone. The graphic illustrates how the battery usage will be tracked and monitored for each test, as well as a cohesive bundle of all tests. This information shall be collected not only during the testing phase, but also as the drones are operating in production, so that the team can address any issues that may arise with specific batteries. Moving on to the system test description. A testing plan will be executed to test all of the functionalities and technical performance consumption of the batteries in the food delivery drone system. Not only will the internal consumption of the battery be tested, but also how the battery integrates with the other components and subsystems of the drone, such as the mechanical claw and the energy required to send the consumer information on their delivery. The test will be conducted by the correct team of functional test engineers. Other stakeholders will have visibility of the outputs of the test for decision making in the future. KPIs will be developed to increase visibility of the test and aimed around the most important qualities. This slide displays some of the battery tests as well as the functional tests that are to be conducted as the system gets designed and developed. There is also acceptance criteria for each test to determine if more work needs to be done before release into production in a real-world scenario. The battery of the integrated system is critical to the success of this project. The plan for the integration testing is broken up into 7 items. The first one being prep, what needs to happen before anything else. The second one is setup, so configuration for the simulation. 3 is the actual testing. 4 is monitor, so real-time observation. 5, analysis, which is done to understand the results. And then lastly, documentation, which is used for future improvements throughout the project. Integration test description. Here are the system requirements directly aligned to the integration test case. Requirements 16 and 17. First requirement is the 1 hour per battery test. The second requirement is at least 30 minutes of flight, and this is for the backup battery to ensure the drone can return to base in case of any anomalies. These risks are also tied to test case number 10.1 to ensure there is traceability. Built-in test. The BIT enables continuous real-time monitoring of key performance parameters such as voltage, current, temperature, and state of charge, providing invaluable insights into battery health and performance. There are 3 primary procedures for the BIT. It is broken up into pre-flight, flight, and post-flight, as shown below.
The production phase of the drone delivery system for food involves the actual implementation and operation of the system in the real-world environment, including the following sections or phases. Number 1 would be preparation and setup. This would include procurement of necessary equipment like drones, ground control stations, and communication systems. Also the setup of operational base and infrastructure, including charging stations, maintenance facilities, and storage areas for the food. Section 2 would be system integration, which is the integration of drones with ground control stations and communication systems, as well as testing of integrated systems to ensure operation. 3 is operational planning, the development of operational procedures and protocols, including the flight paths that they will follow to deliver in each place, the delivery routes, and emergency response plans in case that the drone is not able to deliver the food or that something goes wrong. Also the coordination with local authorities and bodies, regulatory bodies for necessary approvals and permits, including also the FAA for compliance. Training and development, which includes training of the operators and maintenance personnel. Monitoring and control, which would include drone operations, including flight status, payload, delivery, if the drone was able to deliver at the given place. Also maintenance and support, which includes regular maintenance of drones and equipment to ensure optimal performance, as well as providing support to drone operators and addressing any issue. Number 7 is customer engagement. Number 6 is data collection. And for the data collection analysis, it would include performance and analysis of data to identify places for optimization and machine learning, as well as regulatory compliance, which ensures the compliance with all the relevant regulations and standards, and continuous improvement, which implements improvements based on data analysis and feedback to enhance the efficiency of this delivery system. During the phase of maintenance, it was crucial to ensure the continued functionality, safety, and efficiency of the system through regular maintenance. So this phase is divided in the following. First is routine maintenance, which is scheduled maintenance checks on drones and ground control stations, as well as communication systems to ensure that they are communicating between each other and they are working optimally, as well as the inspection of components for replacements and any damaged parts that need to be changed on the drone. We also have battery management, so the monitoring and managing of the health of the batteries to ensure that they're functioning properly and they are charged enough to complete the trips. We also have software updates, which are regular updates to drone software and ground control systems to ensure they are up to date within the latest features for both apps, Android and iOS, as well as testing the software updates to ensure that they work and a customer is happy with them. We also have regulatory compliance, making sure that we are communicating with all the parties involved to ensure that we comply with all relevant regulations and standards, including those by the FAA. And finally, we have customer support, providing ongoing support to customers, including addressing any issues or concerns, having a line for customers to be able to contact us if they don't get their food or if they have any trouble that we need to address, or if the drone has any problems that need to be addressed in the moment. For the disposal phase of this project, we have to identify major components of the system, and some of these components are the carbon fiber body of the drone, the antenna of the drone, the propellers that it's going to use, as well as the battery, and the camera and the flight controllers. All of these ones need to be properly disposed of, either set aside for recycling or reusing in later projects, or disposed of them properly, ensuring that no proprietary data comes out and that all the parts go to whatever they need to go for disposal, either recycling, either a different type of trash for disposal for the battery, and ideally reusability of the camera. For the disposal phase of the drone delivery system for food, it involves the safe and responsible decommissioning and disposal of the system. Once we got rid of the hardware, we have to also dispose of the system itself. So we have to decommission the system. We have to make sure that the data backup and archiving is also decommissioned. The component disassembly is the next phase, and the component inspection, component disposal, and then environmental impact assessment. We have to ensure that all the parts go to the right place. Documentation of this disposal needs to be present as well. Regulatory compliance, a closure report, and a post-disposal monitoring. For the conclusion and discussion, we have system overview. Throughout the course of this project, several key findings and outcomes have emerged throughout this class. class, and the integration of drones into food delivery processes resulted in a significant reduction in delivery times, with some of the deliveries being completed in half the time or as other traditional methods. Looking ahead, there are several recommendations for future projects or improvements to drone delivery systems. These ones include further optimization, ensuring that the risk assessment is more accurate and reliable for taking corrective actions, as well as expanding the range of delivery services offered. And we would like to express our sincere thanks to all of those who have contributed to this project, including the team, the professor, and the class teammates for their reviews to make sure that we delivered a good project. For our lessons learned, we have weather and environmental factors that we have to consider in the future to make sure that we understand the impact on the drone operations, as well as maintenance and support. The drones require regular maintenance more than expected, and an established comprehensive maintenance that support plan is critical for minimizing downtime, as well as customer acceptance. While this type of delivery offers a lot of benefits, we need customers to accept it in order to be successful. So communicating the benefits and the safety measures of the drone to customers is important to build trust and to get to this level as of what drone delivery systems are already achieving. This section highlighted the key lessons learned from the project, and it provided insights for future projects and initiatives in the field of food drone delivery systems.